Hey folks, welcome to the video. It's Arjun here. This video is the first in a series of videos on index theory. Index theory is the study of this quantity called the index of certain operators. These operators are called Fredholm operators, and today's video is on that very topic. It's on the introduction to Fredholm operators and the index. I hope you enjoy. Today we're going to learn about Fredholm operators. It's a particular class of operators that has a property called the index. The index is a key property of Fredholm operators that elucidates their topological properties, and it's useful to areas of mathematics like the study of elliptic partial differential equations and the Atiyah-Singer Index Theorem. It's also pretty useful to physics in the study of instantons, solitons, and solutions to equations on manifolds. So let's get into it. The primary reference that I'll be using today is this book, Index Theory with Applications to Mathematics and Physics. And the prerequisites for today, let's write that down. The prerequisites for today are going to be a knowledge of Banach and Hilbert spaces, as well as some concepts in linear algebra. So this includes knowing quantities like the kernel of an operator, the dimension of a space, whether a linear map is injective, surjective, bijective, and so on. So before we talk about Fredholm operators themselves, let's recall a definition of the set of bounded linear operators with finite norm on a Hilbert space. So we let H be a complex separable Hilbert space, and we also denote B the Banach algebra of bounded linear operators on H. So these operators look like T, mapping from H to H, with finite norm. So recall that for an operator T from H to H, its norm is the supremum of its norm Tu such that U is in the Hilbert space and has magnitude less than or equal to 1. Now, script B is the Banach algebra of these bounded linear operators T on H with finite norm. So this norm has to be finite. Now, an operator in B, so let's start Fredholm operators. An operator T in B is called a Fredholm operator if it has finite dimensional kernel and finite dimensional co-kernel. Recall that the kernel of an operator is the set of all points U and H that get mapped to 0, and the co-kernel of an operator is H quotiented by the image of the operator. So it's essentially the equivalence classes of all points that don't get hit by the operator in the range. So these two quantities have to be finite dimensional, and if they are, then we call this operator Fredholm. Given a Fredholm operator, it makes sense to talk about a quantity called the index. The index of a Fredholm operator T, denoted index of T, is equal to the dimension of the kernel of T minus the dimension of the co-kernel of T. Of course, this is well defined because for a Fredholm operator, the kernel dimension and the co-kernel dimension are finite, so this quantity is also finite. Let's look at an example. So let's look at the example where the Hilbert space is the set of all square summable sequences. So it's the space L2 of Z plus the set of, or really the space of sequences C0, C1, C2, so on, of complex numbers with square summable absolute values. In other words, the sum of all the points in this, of the magnitude squared of all these points in the sequence is finite. On this space, so this is a Hilbert space, and on this space we can define two operators. We call them shift plus and shift minus. And we define them such that the shift plus operator takes a sequence and shifts it one spot to the right, and in the 0th position it places a 0. The shift minus operator shifts a sequence one spot to the left, and it annihilates the 0th component. So we just get C1, C2, C3, and so on. Okay, so these are two operators on this Hilbert space L2 of Z plus. And the question is, are these operators Fredholm? And if they are, what's their index? So we can check that these operators are Fredholm. It's quite simple. Let's look at the shift plus operator case. So the kernel of the shift plus operator, we notice that the set of all points that map to 0, 0, 0, 0, 0, the 0 sequence, is only the 0 point. The reason being, if we want this quantity to be 0, 0, 0, 0, and so on, we want C0 to be 0, C1 to be 0, C2 to be 0, and so on. So only the 0 vector maps to 0. So the kernel is the 0 sequence, which means the dimension of the kernel of the shift plus operator is 0. Now the co-kernel of the shift plus operator, that's the set of equivalence classes that don't get hit by the shift plus operator. We notice that there's only one representative, one sequence representative that doesn't get hit by the shift plus operator. And that's the sequence, so the co-kernel of shift plus is, well, it contains the equivalence class of 1, 0, 0, 0, and so on. Because in the image of shift plus, we have all possible sequences that have a zero, a fixed quantity 0 as their 0th point. So the only sequences that don't get hit by the shift plus operator are the span of this sequence 1, 0, 0, 0, and so on. So it's really the co-kernel of the shift plus operator is the set of, well, this equivalence class really. Or I guess we can say the span of this equivalence class. So this means the dimension of the co-kernel of the shift plus operator is 1. Because these are both finite, the shift plus operator is Fredholm, and the index of shift plus is the dimension of the kernel, 0, minus the dimension of the co-kernel, 1, so it's minus 1. Similarly, shift minus is also Fredholm, but its index is going to be plus 1. Cool. So now that we have defined what a Fredholm operator is, what the index is, and have seen an example, we could ask what are some of the algebraic properties of this index? So how does the index what's the index of an operator if it's acting on finite dimensional vector spaces? Or what's the index of the sum of two operators? Or what's the index of the composition of two operators? So these are some questions that probe the algebraic properties of the index, and that's what we're going to explore next. So let's write down algebraic properties of the index. Now the first question we could ask is, say H and H prime are finite dimensional vector spaces, and we also let T from H to H prime be a linear transformation of vector spaces. The question is, well, there are two of them. Is T Fredholm? And if it is, what is the index of T? In this case, the index of T is easy to find. We know that T is Fredholm because the domain and the range of T are finite dimensional. This means the kernel has to be finite dimensional and the co-kernel has to be finite dimensional. So T is Fredholm. To find the index of T, we recognize that because H and H prime are finite dimensional and T is linear, we have vector space isomorphisms that go from H quotiented by the kernel of T to the image of T and to H prime quotiented by the co-kernel of T. And these are vector space isomorphisms. So the dimension of H minus the dimension of the kernel of T must equal the dimension of H prime minus the dimension of the co-kernel of T. Rearranging, we get that the index of T, the dimension of the kernel minus the dimension of the co-kernel, is the dimension of H, the domain, minus the dimension of H prime, the range. So it's a nice answer to this question. A second question we could ask is, what happens when we add two operators? So we let f from H to H and G from H prime to H prime be Fredholm. In this case, H and H prime need not be finite dimensional. They are Hilbert spaces, and now we can consider their direct sum. So consider f direct sum G and the question is this Fredholm? And if so, what is the index of f direct sum G? Well, this has to be Fredholm because if f and G are Fredholm and they act via a direct sum, then they're acting on a two tuple of u and v, u comma v. So f direct sum G acts on u comma v, where u is an H and v is an H prime, and they act independently. So their kernels must add and their co-kernels must also add. So that means their indexes must also add. So we get a simple result that the index of f direct sum G is the index of f plus the index of G. So it's a very simple result that makes perfect sense. A third question, and the answer to this will not be so obvious, and will take a bit of work to prove. The purpose of this video, or I guess the upshot of what we do today, will be a proof of this third question's answer. The third question is, we let f from H to H prime and G from H prime to H double prime be Fredholm. Then we ask the question, what is the index of G composed with F? G composed with F in this case is also Fredholm, but we're now concerned with finding what the index of this is. The answer to this question is, let's go green. The answer to this question is going to be intuitive. It's the index of G plus the index of F, but it's not obvious. It's intuitive but not obvious. So the rest of this video is going to be proving this claim. In order to prove this claim, we're going to need a tool called the snake lemma. The snake lemma is quite a fun tool. It's an exercise in diagram chasing, so that is going to be fun. And we're also going to be talking about sequences of operators acting on vector spaces. The snake lemma relies on this, so before we get into that, let's first set up a preliminary topic on the sequences of operators, in particular exact sequences of operators. So exact sequences are sequences of let's go with Hilbert spaces. There are sequences of operators acting on Hilbert spaces H1, H2, H3, and so on. And we say that a sequence such as this is exact if the kernel of the k plus 1th linear transformation is equal to the image of the kth linear transformation for all k. So this means that the kernel of T2 must be the image of T1, the kernel of T3 must be the image of T2, and so on. That's when we say such a sequence is exact, when this is the case for all of the operators in the sequence. Now, let's look at some examples of this. Whoops. So some examples. Let 0 here denote the zero-dimensional vector space. That maps into some Hilbert space H1, which then maps via some operator T1 into another Hilbert space H2. This sequence is exact if and only if T1 is injective. Why is this the case? Well, the sequence is exact if the kernel of T1 is equal to the image of the 0 map into H1. 0 maps into H1 at 0. So it just maps 0 to 0. So the image of 0 is 0. So the kernel of T1 is 0, which means T1 is injective. Similarly, we have H1 mapping via T1 into some Hilbert space H2, which then entirely maps into 0. This is exact if and only if T1 is surjective. The reason for this is we want the image of T1 to equal the image of the kernel of H2 mapping to 0, but the kernel of H2 mapping to 0 is the entirety of H2 because all of H2 maps to 0. So the image of T1 equals H2, and that's exactly what it means for T1 to be surjective. If we combine these two sequences, we get 0 maps into H1, which maps via T1 into H2, which then maps to 0. This is exact if and only if T1 is bijective. This makes sense because in this case T1 must be both injective and surjective, looking at the top two sequences, and so T1 is bijective. More precisely, T1 is an isomorphism in this case. A fourth example we can look at is 0 mapping to the kernel of T1, which then embeds into H1, maps into T1, or maps by T1 into H2, which maps to the co-kernel of T1, and then to 0. This sequence is exact by definition. It's exact by definition of the kernel, the co-kernel, and an exact sequence. In this case, we've constructed this sequence so that the image of each map is equal to the kernel of the previous map. So this sequence is always exact. Okay, so now that we know what exact sequences are, let's talk about the snake lemma. The snake lemma is a very helpful tool in proving statements about additivity theorems, so additivity and composition theorems. In our case today, we're going to look at how the snake lemma helps us prove that the index of the composition of two functions is the sum of the indices of those two functions. So in the snake lemma, we consider the following diagram. It's a diagram of sequences of transformations and vector spaces as such. Could take a while to draw. So there's two sequences, two horizontal sequences, like so. And vertical maps between each of these horizontal sequences. We suggestively write f, f prime, and f double prime. Now, in this diagram, we want three conditions to be satisfied. So, the first condition, so three conditions to be satisfied. The first condition is that we want all the horizontal sequences, both of them, to be exact. We also want, instead of writing are exact, let me say horizontal sequences should be exact. We also want the vertical maps, f, f prime, and f double prime should be Fredholm. And the third condition is this diagram should commute. What does that mean? It means that f prime composed with I must equal j composed with f. And we also want f double prime composed with p to equal q composed with f prime. That's what it means for this diagram to commute. Okay, so if these three conditions are met, then we get the statement that the index of f minus the index of f prime plus the index of f double prime equals 0. Now, the proof of this lemma is an exercise in diagram chasing. So you'd have to check, you'd have to use each of these three conditions to snake your way through the diagram and eventually end up at the desired result. I won't prove this theorem here. However, we will use it. This theorem is going to be pretty useful in proving property 3, algebraic property 3 of Fredholm operators, or of the index, to show that the composition of two functions yields an index that is the sum of the two indices of those functions. So let's go ahead and prove. Let's go ahead and prove that claim. Proof of algebraic property 3. Okay, so to begin, we want to construct a diagram that obeys these three conditions and allows us to use the snake lemma to prove property 3. The diagram that we're going to consider is the following. 0 mapping to H, which then maps via some map I onto H plus H prime, which then maps via some map P onto H prime, which maps to 0, and a similar sequence, only this time we have primes and double primes instead of no primes and primes. And the vertical maps between each of these are as follows. We have F here, we have G here, we have G composed with F, direct sum with the identity over here. So this is the following diagram that we're going to consider. And now let's check if it satisfies these three conditions for using the snake lemma. The first condition, that horizontal sequences should be exact. Oh, before we do that, I need to tell you what I, P, J, and Q actually are. I acts on U and H, and it gives us U, comma, F times U, or F acting on U. And J acts on, J acts on some vector V in H prime and gives us GV, comma V. P acts on some vector U, comma V and gives us V minus F U. And Q acts on some vector V, comma W, where W is in H double prime, and it gives us W minus GV. Now, given these four maps, we can check that the horizontal sequences are exact. The easiest way to check this is to show that the kernel of P is the image of I, to show that P is surjective, that way its image is the kernel of the map that sends everything to 0, and that I is injective. This way, its kernel is only 0. And similar statements hold for J and Q. So one can check this, and because that's the case, the horizontal sequences in this diagram are exact. The second condition, vertical maps should be Fredholm. We know F is Fredholm, and we know G is Fredholm. That's by assumption in algebraic property 3, because over here we've let F and G be Fredholm, and because they are Fredholm, we said that their composition must also be Fredholm. So GF is Fredholm. We note that the identity map is also Fredholm. The reason for this is that the identity's kernel and co-kernel are both trivial. So that means they both have dimension 0, and so the identity is Fredholm with index 0. So we know by algebraic property 2, up here, this one, that the direct sum of two Fredholm operators is also Fredholm. So these two give us that GF direct sum the identity is Fredholm. Thus, all vertical maps are Fredholm, just as desired. And then for condition number 3, the diagram should commute. This is also something one can check. You would have to show that GF plus the identity composed with I is equal to J composed with F, and that G composed with P is equal to Q composed with GF plus the identity. So these two conditions can be checked just by acting on arbitrary vectors. In this case, acting on arbitrary vectors U and H, and in this case, acting on arbitrary vectors U, comma V, U, comma V in H plus H prime. So you can check that both of these hold, and so the diagram commutes. So all three conditions are met. That's fantastic. So we can apply the result of the snake lemma, that the index of f minus the index of gf plus the identity plus the index of g is 0. Let's write that down. By the snake lemma, the index of f minus the index of gf plus the identity plus the index of g equals 0. Great. Okay, so we see that we have the index of f here, we have the index of g here. We just need the index of g composed with f. That information we extract from this quantity right here. We recall that we can separate the index of two operators under a direct sum as such, and that the index of the identity is 0 because it has trivial kernel and trivial co-kernel. So this is just the index of g composed with f. Thus, if we rearrange, we get that the index of f plus the index of g minus the index of g composed with f equals 0. And so the index of g composed with f equals the index of f plus the index of g. And we're done. Well, I hope you all enjoyed that. The next video is going to be on the relationship between the index and other types of operators. For example, finite rank operators and compact operators. So stay tuned for that. Until then, please like, subscribe, and leave some comments down below. I'm always open to feedback, suggestions, and corrections. I'll link my notes in the description as well as some references. I'll see you all in the next one.